Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on Statistical Methods in Hydrology. This video is part 3 of 4 on the topic of index flood regionalization, and we'll discuss estimation of regional probability distributions. Let's get started. Creating regional distributions is the primary goal of index flood regionalization. In general, there's a 4-step process for each region that involves iteration between the first 2 steps. We will use precipitation frequency analysis primarily in this discussion, but other meteorological variables are able to be used in the same way. The first step of the process is to create a region containing several sites, with the selection of the sites based on physical properties. We want to combine together sites that, based on our understanding of the physical processes that create extreme rainfall, should be similar. We haven't looked at the statistics of these sites, only the physical properties such as location, elevation, climatology, and so on. The second step is to use statistical tools to evaluate if the region is sufficiently homogeneous. If the region is reasonably homogeneous, we can go to step 3. If not, we need to choose different physical criteria for the grouping and rearrange our sites. Step 3 is to compute the L moment ratios for the region based on the sites inside the region. Finally, step 4 is to choose a probability model for the region and to use the regional L moment ratios to estimate the parameters for that distribution. Creating regions using a physical basis is important. This ensures that we are grouping together sites that plausibly observe the same thing. A good place to start in the United States is the National Weather Service climate regions, which are used as reasonably similar groupings of meteorology broken up by state. There are limitations to these regions, such as discontinuity across state boundaries and differences in the way they are drawn by state, but as a first attempt, they're generally consistent. After initially grouping sites using a high-level grouping like the climate regions, we should refine those groupings. Usually, these climate regions are quite large and may contain an impractical number of sites. A rough guideline is that regions should contain 20 to 30 sites per region, but this number can vary if the sites are more highly correlated or more dense, such as in urban areas, and so on. When refining the regions, here are some physical variables worth exploring. Location is a good first choice, again pointing back to Tobler's first law. We can quantify location in latitude and longitude or in planar coordinates. Elevation is a critical part of precipitation intensification in many places and can be a good divider of the behavior of sites between valleys and mountains. Climatology, or long-term meteorology, can give an idea of the variation in weather on a finer scale than the climate regions do. Mean annual or seasonal temperature, or precipitation, can be used as climate normals used for making divisions. Geographic features that affect the formation and intensity of rainfall, such as the ocean or mountains, can be identified by using the distance from a coastline or a mountain range. There are other variables that you might consider depending on your application, but these are some of the most commonly used ones. Here is an example of a collection of sites shown on top of the National Weather Service climate divisions. If we were starting a frequency analysis in this area, we might start by grouping together the sites by climate division. The one on the far left in the west is the Olympic Mountains region, which contains 18 sites. The mean wintertime precipitation in this region is 1,435 millimeters, which is about 56.5 inches. Across these 18 sites, there is a total of 1,037 station years of record. That is, if you add up the record length for all of those stations, the value is over 1,000 observations. If we tested this region and found that the L moments for the annual maximum series for these 18 sites had an acceptable amount of variability, we might consider this a homogeneous region. If not, we might start to divide up the stations in this region to find homogeneous groupings and consider combining in stations from nearby regions if it makes sense. Although spatial proximity is one of the best predictors of whether or not sites will be similar, in some areas there are other more dominant features that control the behavior of stations. The points in the plot on the right are plotted by longitude and latitude, and the 4 colors represent 4 regions carved out of this dense network of stations. These are all stations within 100 miles of Whittier Narrows Dam, and the watershed above the dam is roughly in the dotted box. There is very high station density in this area, so all of these sites are close together, relatively speaking. However, the San Gabriel Mountains have a pronounced effect on precipitation in this area, and depending on the site's location relative to the mountains, the rainfall characteristics can change drastically. The regions here are primarily defined by their elevation and which direction the slope of the mountains face. The region in green is the collection of sites at higher elevation on the windward side of the San Gabriels, where the heaviest rainfall is possible. There are also some sites in the green region atop the coastal mountains west of the city, which also experience heavier rainfall than the surrounding area. These are examples of non-contiguous regions. They tap into the key properties of the rainfall extremes in this area, which spatial proximity alone can't explain. Homogeneity is a measure of the similarity of the statistical properties of the observations of sites in a region. It is measured by comparing the amount of variability of the L moments of the sites to a standard dependent on the sample error. This produces a single statistic that tells us whether the variation is too high or acceptably low. If we find that the variation is too high, then we need to reformulate this region and likely others around it. If we find that the variation in the site L moments is low, and we design the region using physical means, then the region is probably homogeneous. The H statistic measures heterogeneity, the amount of variability in the site L moments. We assume that low values of H associated with a low likelihood of heterogeneity means that the region is homogeneous. H is computed by comparing the spread of the LCV for the sites against a simulated perfect region. The so-called perfect region is set up to look just like the region that you're testing. It has the same number of sites, the same record length at each site, and the same regional probability distribution. It assumes the sites are perfectly uncorrelated, however. Monte Carlo simulation is then used to create artificial periods of record from this perfect region. For each period of record, the standard deviation of the perfect region LCVs is computed. After a large number of these artificial periods of record are created, the observed spread in the site LCVs is compared to the simulated spread. If the observed spread is too big, the heterogeneity measure H is high and the region is probably heterogeneous. If H is low, usually under 1, then the region is probably homogeneous. If H is between 1 and 2, then the region might be homogeneous, but regional refinement is beneficial and is likely to improve the model. Regions with values greater than 2 almost definitely need to be refined. If you detect that regions are heterogeneous, then there are 3 typical courses of action, which are taken iteratively with further checks of the H statistic. You might try to split a region into parts, for example, splitting it in half by the upper half and lower half of annual total precipitation. This works best if your region has a large number of sites to start. On the other hand, it might make sense to combine up some smaller regions into a larger region based on physical characteristics. Occasionally, you need to work at the level of granularity where you are moving individual sites around between regions. Cluster analysis can be used to identify subgroupings using physical predictors with some success. However, an automated method like this doesn't replace your judgment. Another tool that helps identify stations that might not belong in a region is called the discordancy measure, or D. D measures how far a site's L moment ratios are from the region average. If the D statistic for a site is too big, it might indicate a few things. One is that the site belongs in another region. It might mean that including that site in a region is causing it to be labeled as heterogeneous. It can also identify a site with an error because its L moments are affected by an error in the data. It is worth looking in more detail at sites with high D statistics to see what might have caused this value to be so large. Here, we introduce the L moment ratio diagram. The LMRD has a ton of information. It's a plot of L skewness on the x-axis and L kurtosis on the y-axis. First, the LMRD shows the relationship between L skew and L kurtosis for a number of probability distributions. 2-parameter distributions have a fixed value of L skew and L kurtosis and show up as points labeled with letters. 3-parameter distributions have a value of L kurtosis which is dependent on L skew and they show up as colored lines. Next, you can look at the behavior of individual sites and see how closely related the L moment ratios for sites in a region are. If your region has a large spread in points, as is shown here, it's likely that your H statistic is going to be large for that region. Sites with a large D statistic are likely to fall far from the center of this grouping. The LMRD can help you identify a probability distribution that might be able to model your data. If your points tend to cluster along one of the colored lines, that 3-parameter probability distribution might be a good model for your data. Another feature is where the central tendency of the data is. The center of mass for the points, weighted by the record length for each site, is the region average L skew and L kurtosis. The region average L moments LCV, L skew, and L kurtosis are computed as weighted averages of all of the sites in a homogeneous region. These L moments are weighted by the record length of the sites used in the computation. This is actually a very similar mechanism to how regional skews are done for streamflow. Regional skew weights a regional value with the at-site value by the mean squared error of each value. The MSE is inversely proportional to the record length. These regional averages are done the same way. The region average L skew, for example, is influenced more by site L skew with longer records, which are expected to have a smaller sample error and therefore smaller MSE. Here is the LMRD again, and instead of plotting each station as a point, each station is plotted as its record length. For example, the site in the upper right where the arrow is pointing has a record length of 40 years. The regional average L skewness and L kurtosis are computed, and then the resulting point is plotted on the LMRD. Sites with longer record lengths have more leverage on the overall computation. These data are pretty spread out, but the weighted average finds a place near the center. Notice also that the longest record stations tend to be towards the middle of the cluster, with the shorter record lengths generally further away. This is a symptom of sample error. A probability distribution can be applied to a region by estimating its parameters using the method of L moments. The method of L moments is the same as the method of moments that we've talked about before, except instead of measuring the moments using conventional product moments, we use L moments instead. Probability distribution parameters can be expressed in terms of L moments so that a distribution can be fit to the sample. In the back of the Hosking and Wallace book, Appendix A has the distribution parameters for several probability distributions expressed in terms of the L moments. The example here is for the generalized Pareto distribution. You could see how you would plug in the region average L moments to get the parameters of a distribution that represents the region. In R, there is a package called LMOM or LMOM that has a number of distributions built in, which will give the parameter estimates when given a set of L moment ratios. It makes fitting distributions to samples using L moments very, very easy. We've called the procedure that we're applying the index flood method for a while now without really explaining where that came from. Index flood regionalization assumes that the sites in a homogeneous region have the same probability distribution except for a site-specific scaling factor. This scaling factor is called the index flood. What the index flood allows is for smooth systematic variation of climatology or other gradually varying impacts to play a role in estimating the frequency curve. When this method was originally applied for streamflow, the index flood was also used to capture variation in drainage area because the magnitude of floods for a gauge are related to the drainage area of the watershed above them. Most of the time, the index flood is the mean annual maximum value, which is also the L-mean statistic L1 for the site. Other index floods occasionally used are the median or a trimmed mean. From here on out, we will assume it's the mean annual maximum because this is the one that's overwhelmingly common. When making predictions at a site based on a regional distribution, there are two parts that are needed. The first is the index flood for the site of interest, usually the mean annual maximum event, and the second part is the regional growth curve, which is a special way of representing the regional probability distribution using the index flood method. The regional growth curve is a dimensionless way of representing the regional probability distribution. If you get quantile values from a regional growth curve, these do not represent the regional rainfall. It represents the multiple of the index flood associated with that frequency. Such multiples are called regional growth factors. The RGC, regional growth curve, is estimated so that it has an LCV, L skew, and L kurtosis equal to the region average, and then a mean of 1. This means that when you get a value from this probability distribution, it tells you how much larger or smaller this frequency is than the index flood for any site. In this example, we want to take a regional growth curve and apply it to a site that has an index flood of 2.5. To get the at-site frequency curve, we simply multiply the RGC by the index flood to get the at-site frequency curve. Why would you want to use the index flood method? Well, there are two main benefits to using it. First, estimation of the regional probability distribution is very straightforward. the mean is set to 1, and the weighted average LCV, L-skew, and L-kurtosis from the sites in the region are used. Then, the parameters can be estimated using the method of L moments. Second, the index flood method can be used to make frequency estimates where there are not sites. Two properties are required in order to make estimates at ungauged locations. First, the location has to be assigned to the appropriate region, and second, the index flood needs to be able to be estimated there. Luckily, the index flood from meteorological data, such as annual maximum precipitation, tend to be predicted well using linear regression based on climatological factors, which can be drawn as a continuous map. Here is an example from the Whittier-Narrows Dam Safety Study. We're able to predict the index flood, which is the mean annual maximum precipitation, from PRISM precipitation data. This means that anywhere inside this region's boundaries, we can predict the precipitation frequency relationship by estimating the index flood everywhere using PRISM and then applying the regional growth curve for that region. Unlike the guidance we get in Bulletin 17, there's no prescribed probability distribution for us to use. It's up to us to choose the appropriate model for our data. We can start by looking at the L-moment ratio diagram again, as it does offer some guidance based on the site and regional L-skewness and L-kurtosis. We can look to see if there's a distribution that the region average falls close to, or if there's a general overall shape to the points created by the sites in the region. An alternative approach is to turn to extreme value theory, a topic we've already seen. If our samples are reasonably homogeneous, not only as a region, but also by cause, we can apply some of the asymptotic results that we get from extreme value theory. This means that in well-behaved scenarios, annual maximum data tend to be modeled well by the generalized extreme value, or GEV distribution. Partial duration, or peaks over threshold data, are modeled well by the generalized Pareto, or GPA distribution. And annual maxima in situations where there are few events per year can be modeled by the kappa distribution. On the L-moment ratio diagram, we can see that several 2- and 3-parameter probability distributions are available for describing the data. In this situation, we see that the data are quite scattered and the region average isn't very close to any particular probability distribution. The GEV and generalized normal distributions, and possibly the Gumbel distribution, are potential candidates. The kappa distribution has 4 parameters and is very flexible. It can model L-moment ratio pairs anywhere in the orange region that I've overlaid on the plot. However, with small samples, the potential for overfitting is possible. You may be fitting a model that fits the data really well, but doesn't offer any out-of-sample power. Using the kappa distribution is acceptable in 2 situations. 1, you are estimating its parameters using extreme value theory basis and have started with a partial duration analysis. Or 2, you estimate the 4th parameter of the distribution using all of the regions in your study area, not on a region-by-region basis. In some studies with many regions, we estimate the 4th parameter of the kappa distribution, called the H parameter, for the entire study area and choose a single H parameter for the study. This effectively creates a 3-parameter distribution, which shows up as a line on the LMRD. When we do this, then regions would have distributions that fall on the thick line, but maybe anywhere along that line. In this example, we estimated the kappa distribution H parameter from all of the regions in the study area, and plotted this result as a thick orange line. The region that we've been looking at has a region average very close to the resulting distribution. In this video, we discussed estimation of regional probability distributions. 3 key points to take away from this video are: creation of regions in a regional analysis is an iterative process. The regions we create should be physically based, seeking to explain the physical cause of variation in our observations. And the index flood regionalization method lets you make estimates for the frequency curve anywhere you can measure the index flood. Thanks, and tune into the next video in this series on index flood regionalization to learn about applying regional frequency estimates.